Good morning, everybody. My name is Ijah. I am the architecture critic for Building magazine, but for this morning's purposes, I'm also the chair of this morning's webinar. The title of this morning's webinar is Sustainable Concrete, Design Solutions for Low Energy and Material Efficient Office Buildings, and it's brought to you today by Building in association with the Concrete Centre. Right, today's talk is going to focus obviously on the area of sustainable concrete, using two particular recent office blocks in central London as a kind of trigger for our debate and conversation this morning. These two recent offices in central London are 5 Pancras Square and 240 Blackfriars, just behind us here, and both of these are widely seen as superlative examples of the innovative and pioneering use of sustainable concrete. So, during this morning's webinar, we're going to be hearing from the architects and structural engineers who worked on these buildings, and they're going to be sharing with us their knowledge and experience as well as their expertise in sustainable low-carbon concrete and how it can be efficiently and successfully utilized. We're also going to be hearing expert opinion and input from the Concrete Centre, who are going to use their technical expertise to expand upon the various design and aesthetic options available with the use of sustainable concrete with regard to elements like exposed soffit options and wider energy performance within buildings. Right, we have an esteemed panel even of experts joining us this morning who are going to impart their knowledge to you. We're going to be hearing from James Allison, who is an associate at Bennett Associates. Bennett Associates actually designed 5 Pancras Square. We'll also be hearing from Jerry O'Brien, who is the design director of AKT2 Consulting Engineers. The AKT2 was in the unique position of having worked on both schemes, so they'll obviously no doubt have invaluable insight into how low-carbon sustainable concrete can be applied. And last but not least, we'll be hearing from Tom DeSaul, who is a building physicist at the Concrete Centre, and they'll also be giving us their technical expertise on the options and potential of the use of low-carbon sustainable concrete. Right, so essentially we're about to begin. Please feel free to ask any questions. Send us any questions during the actual, while the speakers are speaking, and at the end, when they've all spoken, we'll collate questions and we'll present them to the speakers directly. So you have your opportunity to present queries and questions to the speakers directly based upon what you hear them saying during the webinar. Also, if you're on Twitter, you can feel free to follow the chat at #ThisIsConcrete. Right, with no further ado, that's enough from me for now. We're going to be hearing from the first of our esteemed panelists, who is James Allison. James Allison is an associate at Bennett Associates. Bennett Associates designed 5 Pancras Square. So obviously, James is going to be able to give us an invaluable insight into how sustainable concrete was applied within that project and hopefully extrapolate wider principles which we can all relate to with regard to use of the material. So, no further ado, I'd like to introduce James. Thank you.
Thank you very much. Great. Well, I'm here to talk to you very quickly about the sustainable uses of concrete in 5 Pancras Square, which is a new building for the London Borough of Camden at the King's Cross Regeneration Master Plan site up in North London. So to start off with, I thought I'd give you a couple of quick project details, which you can hopefully see on your screen in front of you now. We were very lucky to work with an excellent team of consultants who worked collaboratively to achieve a building with the highest standards of environmental sustainability. And over the 2.5 years on site, we were able to procure a building of the highest BREEAM standards, outstanding, with a score of just over 93% during the design stages. And we're hoping to exceed 96% with its post-construction score. So moving on. Before we get stuck into the detail of the concrete, I thought it'd be very useful to give a quick overview of the design itself. So 5 Pancras Square occupies a very compact corner site, outward facing over the London Borough of Camden. It occupies the northwest corner on Zone B of the master plan, which was actually the first phase of the overall master plan to be developed. It's bound by Pancras Road on the west and Goodsway on the north. It sits on an area of land directly between King's Cross Station and St Pancras Station. The building accommodates a diverse range of functions over its 14 floors. At the lower level we have 4 floors of public floors, including a basement swimming pool. At lower ground floor we have a fitness suite, and above that we have council services, including customer services and a public library. Hopefully on the left hand side of the screen there you can get a glimpse of what those spaces look like. Sat directly on top of the office floor, on top of the public floors, we have 10 floors of office accommodation, and these are distinctly clad in this bronze anodized aluminium cladding, which contrasts with the precast concrete cladding on the public floors beneath. The office floors have a number of terraces which wind their way up on the north and west facades to animate the building and to introduce natural daylight into those spaces. We have to see on the top left there a view of the typical office floor. The introduction of natural daylight was something we were very keen to have in the building. We have exposed concrete soffits which have been painted, and suspended light fittings and primary services. Connecting all of the office floors, enhancing that natural daylight and the interconnectivity between the office floors, we have a top-lit central atrium with a feature staircase which adds for that interconnectivity between floors. The section on screen now also helps explain the distribution of spaces within the building. At lower level we have 4 floors of public facilities, as I've just explained. On the north side, which is to the left of the section, we have a double height space which connects the library with customer services. On the right hand side, the south side of the building, we have a triple height entrance space which is entered into from Pancras Road, and this connects through into a double height entrance space from Pancras Square. Set above that we have 10 floors of offices which are interconnected with a central atrium, a number of terraces on the north and west, and 2 floors of plant accommodation at the roof on the south side. So where does the concrete come in? We were keen to use concrete in the building as much as possible, and hopefully this slide helps you all understand where the concrete has been used. From the outset we were keen to use concrete, and this was driven by a number of factors. A mix of construction methods and exposed finishes. So running through very quickly, we've used concrete in the foundations, retaining walls and cores, all of which is not exposed in the complete works. External cladding to the public floors, this was the light coloured precast concrete which we saw in the slide a couple of minutes ago. Transfer structure, which is actually one of the key elements of the design, I'll come on to talk to in a little bit more detail about, but this is a key, or demarks a key split between the public and private accommodation above, transferring out the office columns on the floors above, suspending the public floors beneath, allowing for a column-free swimming pool in the basement. Above the transfer structure we have the office floor slabs, all done in situ concrete using a modular formwork system. All of the slabs are exposed and painted. The office columns were done as precast concrete columns with steel reinforcements, and these have been left exposed in the completed works. So these elements look something like this. And these were all kind of photos taken of those various elements during the stages of construction. Bottom left we have the slip-form core arising from the base of the building. You can just start to see the steel structure for the transfer structure emerging at its base. To the right hand side of that we have a view from the lower ground floor looking up to the exposed concrete of the transfer beams, and you start to get a sense of the suspended structures beneath that. To the left hand side of that image you can just start to see the lift landing which is suspended beneath the beams. To the right hand side at the bottom we have a view of the lower ground floor entrance, which is framed in this light coloured precast concrete, contrasting in colour with the office floors above. To the top of the image we have, on the right hand side, we have a view of the retaining wall which was propped in its temporary state, and this retaining wall ran all the way around the B zone until it was filled up with the various buildings. To the left hand side of that we have a view of the office floors and in construction. I think the concrete slab had just received its first coat of paint there. So we were keen to focus on 4 areas and utilise the sustainable qualities of concrete where possible. These were driven by a number of factors ranging from site-specific requirements to satisfying the various BREEAM aspirations. The use of exposed thermal mass and how this relates to operational energy efficiency were key drivers of the design from the outset. And given the fact that the day-to-day operation and construction of UK buildings is responsible for nearly 50% of the UK CO2 emissions, we were keen to do our bit to reduce the carbon footprint of the building. So I think the key point to mention here is that site factors really drove the environmental design response of 5 Pancras Square. Its location on a very busy corner site next to a noisy station and bounded by 2 heavily trafficked roads meant that natural ventilation with opening windows wasn't really appropriate. So we were driven to a mechanically assisted displacement ventilation solution which operates during the daytime, and the building is purge ventilated at night when it's quieter through opening windows and central atrium when required. So the exposed thermal mass is put to good use within the building. The structural frame is used to minimise the operational energy. During the warmer months, the building is cooled overnight to ensure that the internal environment is occupiable the following day. And during the colder months, the slab and the concrete frame is used as a heat store to again make sure the building is a good environment to be in when occupied. I think it's probably worth mentioning at this point that the Council, London Borough of Camden, aim to cut their carbon emissions by approximately 64% during the projected, during the kind of life of the building, with a projected annual saving of just over £500,000 per year. Next up, resource efficiency. I think we were kind of keen to maximise this as much as possible. It's fortunate that limestone, the raw material in the cement used for concrete, is the most abundant mineral on the planet, and that's great for everyone who likes concrete, but we were very keen to maximise the use of secondary and recycled aggregates as well. So 32% of the concrete used in the building is done with secondary aggregates which are used in the construction, and this is great because it exceeds the BREEAM target, which is 25%. So the recycled content is produced from stent and generated during the extraction of china clay, and I think the majority of this, 21%, is used in the construction of the floor slabs. So you can see there the installation of those floors, guys on site. Another key characteristic of concrete which we were keen to make the most of was that in fact it's durable and it has a long life. Concrete is a strong material, it's easily repaired, and it's arguably robust and more adaptable than, well, in comparison to lightweight structures which are often associated with flexibility, and flexibility is one of the key brief items that Camden wanted within their building. Concrete offers other benefits including fire resistance and excellent acoustic properties, so all of which helped when we were designing the building. I think on this final slide I wanted just to capture a couple of other key features of concrete which we felt added value and were brought about through innovative ideas and kind of innovative construction methods. The transfer structure to start off with. So middle bottom there you have a view of the transfer structure halfway through construction. This structure was quite an impressive piece, and we always wanted to make the most of it and celebrate that within the building. So we chose to expose it so people could start to understand what structural gymnastics were happening within the building, and I think improving the legibility of the structure helps people appreciate what's happening and appreciate the building that they're in. The structural arrangement allows also for good open spaces with excellent levels of natural daylight, so that the building becomes a space that people want to inhabit. Facade expression, this is very much linked to the transfer structure itself. You can see on the bottom left image there that the precast cladding panels align with the internal transfer beams, and this then helps reinforce the legibility of how the kit parts of the building start to work together. Soffit formwork systems and slip form construction of the building cores. I mean, very different construction techniques, but they offered very similar kind of benefits, which included a very quick, repetitive form of construction, and ultimately a cost-effective means of constructing the building. And finally, we feel that the use of concrete helped enhance the office environment. What we have are exposed concrete soffits within the office. And this, when painted white, really helps improve the quality of daylight within those spaces. And I think also by suspending the light fittings and primary services, those spaces feel very lofty compared to buildings that generally have kind of fully enclosed suspended ceilings. So ultimately we were trying to create flexible workspaces, but spaces that were good to inhabit. So I think in summary, I think this shows that sustainability is not simply related to the energy credentials of a building, although they're very important. It goes way beyond. And we hope that 5 Pancras Square offers a balance between environmental, social and economic sustainability, and that the use of concrete has enforced this balance. Thanks very much.
Great, James. Thank you very much. Very insightful presentation there. I'll just remind everybody that please send through questions. I know some of you started doing that already, and we'll be able to present these questions to the panel after they've all finished speaking. Right, next up we have Jerry O'Brien. Jerry O'Brien is Design Director at AKT2. AKT2 were in the unique position of working on both of the buildings which we're focusing on this morning. So Jerry too will no doubt have an invaluable insight into how low carbon sustainable concrete can be applied on those kind of projects. Right, Jerry, over to you.
Hi, good morning. I've chosen 240 Blackfriars to talk about actually this morning because it is relevant in a number of ways. Firstly, we're sitting directly opposite, and secondly, it's going to be Building Magazine's home in a week or so's time. It was commissioned by Great Portland Estates with AHMM as the architect and built by Mace with Burn Brothers doing the frame, and is an excellent example of a high-performance building in which we've used concrete to solve many problems. This is a picture of the building as it currently stands on site today. And the site is located just to the south side of the Thames in central London. It has many of the typical issues that you find in central London sites, in that it has a high water table, slightly tidal, affected by the Thames. It has railway lines and major roads running around the site. And the site was previously developed, which meant there were a number of obstructions already on the ground that we had to deal with as we went through the process of building it. The original conception by HMM drew parallels with forms that are found in nature, particularly referencing blocks of amber that they had uncovered. They then used this as the inspiration and responded to the particular context of the site by putting a number of strategic cuts through the building which maximised views to the city of the sky and really made a much more close relationship between the public realm at the base of the building by cutting it back slightly. And the next slide just shows an exploded version of what the final structural solution was to this building. For us, one of the big questions obviously was the right solution for the structure. Now, clearly, for sustainable buildings, it's not about frame alone. It's not about the materials that go into it alone. They must, firstly, above all else, be efficient. And the BCO, the British Council for Offices, publishes guidelines that direct you in the direction of good design. Historically, in central London, spec offices tended to have quite large column-free grids of perhaps up to 15 to 18 metres, but that's now become less frequently done, with the grid generally being taken to be the right size that would allow the building to function without any loss of functionality, whilst reducing the amount of materials that have to go into constructing it. So this is a picture of a typical floor plate in the building. I say typical because, slightly tongue-in-cheek, as there are no floor plates which actually repeat up the building due to the geometry. But it's generally based around a 9 metre by 10.5 metre grid with 9 by 6 metre grids around the outside. And in assessing what would be the most appropriate approach to the structural solution for this building, we looked at many different options. Steel options were put on the table, but at the smaller grids of sort of 9, 10.5 metre, they're not really a competitive solution. And when we look at the longer span solutions, what we find is that within the same or the equivalent building height, we can actually get 1.5 extra floors if we opt for a concrete solution. And so the solution which was adopted, was a post-tensioned flat slab. And this was preferred because it minimises the overall flow zone, therefore maximising the floor-to-ceiling zone, and it minimises the amount of material inside the frame, which is much more important than picking around the edges by using cement replacements and secondary aggregates or such like. However, we did of course use cement replacements in the concrete, and these PT slabs have got 20% GGBS in them. We always take a holistic view when we look at these at the options, and what we found particularly interesting in this case is that for a very small increase in weight in terms of what is transferred to the foundations, we get a floor plate which actually performs much better than a steel equivalent would do, because it has better vibration characteristics, it has better acoustic characteristics. And down at substructure level, we also took the opportunity to review a number of options to make sure that we had the optimal solution, which actually was very buildable, minimised the amount of materials that went into the construction. And here we were able to take the opportunity to maximise cement replacements and recycled concrete aggregates, because these were not exposed elements, and strength gain was not so critical. This was true also for the embedded retaining walls, for which we adopted a secant pile wall because of the water table issues. Interestingly, for this particular building as well, we had a number of challenges set by the core construction. For a floor plate of this size, which is around 1,200 square metres, a very efficient planning operationally for the building is to have a side core. Now, the side core comes with a number of problems for us to unlock, however, because what it means is that the majority of the load of the building goes down one side of the core, as it carries the majority of the floor loads, whereas the other side is simply carrying its self-weight. And what this does is it results in the situation where the core actually curls under vertical loads. To resolve this, there were a number of options open to us. The first one was to simply enlarge the core so that it was big enough that we could plumb the lift shafts from top to bottom. So this would have resulted in quite a large loss of net floor area. Secondly, we could pre-stress the eastern edge, the lightly loaded edge of the core, so that we equalise stresses throughout the core. And the third one, the one which we actually ended up doing, was to preset the core, aiming at its theoretical position in the air and feeding back through the process how the building actually responded as the floor loads were put on. And using this approach, we actually managed to get the core at the top within 7 millimetres of its desired position. I think this building is a great exemplar of the versatility of concrete, because there are a number of complexities in it. At the base of the building, the entrance required some pretty large column construction, and these are some drawings of the formwork which Burn Brothers did. Here you can see the columns themselves. They're over 9 metres high, and they're inclined, and they have to be visual grade. So for this, the solutions that we developed with Burn Brothers was to use very, very high quality steel shutters and bottom pump them so that we could ensure that we would have excellent quality finishes the whole way up through the column. Towards the top of the building, we have some pretty complicated connections and junctions, which is due to the coming together of the geometries through the cut planes defined by the architecture. And the architecture actually has quite a strong logic to it, where the roof plane, which is shown in red in these diagrams, is actually steel, and it's an extension architecturally of the roof coming down the face, and bringing together the concrete frame coming up from below and the steel frame from above was a real challenge. And in one location that we had to develop solutions which allowed high visual control in terms of the quality of the concrete, cast-in elements that allowed us to connect to the steelwork, and very, very high tolerance, because these were all pretty much right in the line of sight. So we had 3 millimetre tolerances within some of these connection details, which became affectionately known as the witch's hat. The other thing about this is that we precasted these elements because they were actually very large, and they were being installed 90 metres up in the air. So the act of installing formwork and falsework at this height, you can see across here the precast frame on the front edge, the witch's hat at the top left, and the 54-metre spanning truss over the very top of the building that collects it all together. And so using precasted solutions, we ensured that it could be built very, very accurately. This building gets a lot of airplay about BIM, and I thought that I would just very quickly touch on it because we did use full BIM on this project. It was successful. I don't think that we drilled any new holes in the floor slabs. It was properly integrated into the design, both structurally and from an M&E perspective. Of course, it's all about the timing of the information, but it did fundamentally make the build more buildable and also reduced waste on site.
Great. Thank you very much, Jerry. Very interesting presentation. Once again, as I said, please feel free to carry on asking questions as you are, which will be presented to the team at the end of today's talks. Right, last but not least, we will have input now from the Building Centre. We're going to hear from Tom DeSaul, who's a building physicist from the Concrete Centre, and obviously the Concrete Centre are experts in the use of concrete, sustainable concrete, and Tom is going to make particular reference to the advantages that can be presented from exposed soffits and how these can be utilised for cooling. So without further ado, over to you, Tom. Thank you.
Thanks, Ike, and good morning to everyone who's listening in. I'm going to talk very briefly about the use of exposed soffits for cooling, which I think ties in quite well with James's talk actually earlier on 5 Pancras Square, which uses this technique. And it's a technique that's becoming increasingly popular in mainstream office design, and here you can see some speculative offices that have all got exposed soffits as part of their low energy cooling strategy. So I guess really the main driver is to cut the energy required for cooling, but I think also exposed concrete or visual concrete is becoming increasingly popular with architects and clients. And I think the third driver is that a lot of the large financial institutions who are behind these speculative office developments are very keen to future-proof their properties. And when I say future-proof, I mean in relation to rising energy costs and climate change and rising temperatures. And of course, a key way to do that is through low-energy design. And thermal mass and concrete is playing an increasingly important part in that. So how does it work? Now, you may or may not know that we lose about 60% or roughly 2/3 of our body heat through radiation. But in order to be able to do that effectively, it's very important that we can physically see surfaces that are around us that are cooler than we are. And of course the soffit is ideally placed for that because firstly it's not very far away and distance is an important factor. The nearer the surface the better. It also has a very large surface area which helps, and of course if it's made from concrete it's going to have a high thermal mass, and that's important because it means it can absorb a great deal of heat without actually warming up significantly. So in other words the soffit temperature remains quite stable, probably only varies by about 1 to 3 degrees over the course of the day. So even towards the end of the day it's still sufficiently cool to carry on absorbing heat. In other words, we can radiate heat to it all day. Now you do have to get rid of that heat that's accumulated. That's generally done at night using the cool night air to draw the heat back out. But you can do it with water as well, and I'll come on to that in a moment. So the principle is very simple, but there's lots of different ways of exploiting it, lots of different types of floor. And these are the main ones on this slide, and I've tried to group them together into sort of 3 general groups. So first of all, at the top there you've got systems that rely on ventilation to regulate the slab temperature, and you can have the simplest option on the left there, which is similar to the previous slide, but you've just got a flat soffit, windows that you can open at night to cool the building down. Then you've got mechanical systems. Typically these are mixed modes, so you've got a combination of mechanical and natural ventilation, so you get the best from both techniques. And I think it's fair to say this is what most buildings will use, in other words a mixed mode system. Now more recently water-cooled soffits have become very popular, and you can see that in the middle of the slide. It's where you've got polybutylene pipework embedded just above the surface of the soffit, and that's supplied with chilled water, quite often from boreholes, and the water from boreholes comes up at just the right temperature, about 12 to 14 degrees, but you can use heat pumps as well and conventional chillers. Now the advantage of water cooling is you get a higher cooling output and really good level of control. You're not reliant on nighttime cooling to regulate the soffit temperature. And so it's a hybrid system really. You've got a combination of passive and active cooling. And then finally, another option which is also quite popular is to use chilled beams suspended from a concrete soffit. And this is popular in new build and refurbishment projects as well, where you've got an old 1960s or 1970s concrete frame building that you strip back to the frame and taken out the full ceilings, painted the soffits and put in some multi-service chilled beams. Now I could go on about these for hours and be quite boring, but I haven't got time for that, and there's no need because we have got a marvellous publication, which is the next slide, if I can just get it up. Come on. There we go. And you can download this from our website, and it's got all of the systems I've just shown you and loads of case studies as well. And I'm just, in the last few minutes, just going to pick out a couple of case studies from this guide, the first of which uses an exposed soffit. Could be flat, could be coffered like in the drawing here, and we use coffers for structural reasons, as you probably know, to reduce the weight of concrete, which in turn allows you to increase the span. But from a building physics point of view, there's the added bonus that it increases the surface area of the soffit, so you can get more heat in and out of the concrete and work the thermal mass a bit harder. And if you combine that with underfloor ventilation, which you can see here, now you've effectively doubled the surface area through which you can get heat in and out. So you can use depths of concrete, sort of 300-400 millimeters. And that's a very popular option. Get around 35 watts per meter squared of cooling, which is fairly modest, but it's certainly enough to maintain comfortable conditions in buildings with good solar shading and fairly small internal loads. And a good example of this technique can be found at 55 G Street in London, which is an 8-storey mixed-use development. And if you look at the photo on the right, first of all, you can see it's got a flat concrete soffit with rebates or recesses cast in for the lighting, which is a nice feature. And another really nice feature is the deep brick piers, which provide excellent solar shading, but also they allow some natural ventilation because they're made from perforated bricks. And if you look at the photo on the right again, you can see there's a narrow vertical door, which is a ventilation panel that the occupants can open to get a little bit of extra ventilation. Right, and just very briefly, here we've got a couple of water-cooled soffits. These are both precast options. Top one's a hollow-cast slab. Of course, all the pipework's embedded in the soffit at the precast factory and pressure tested there, so once it's delivered to site you just connect it up and you're good to go. And at the bottom we've got a lattice girder soffit. That's where the soffit's precast, and you add in situ concrete on top once it's in position on site. As you can see, you get a pretty good cooling output with these, around 65 watts per meter squared. And as I said earlier, you've got a very good level of control as well. And the lattice girder option at the bottom there is used at the business school at Manchester Metropolitan University, which was quite a large project. I think it's about £65 million, completed in 2011. And here you can see one of the floor units being craned into position. These were made by Hanson, and if you look on top you can see polystyrene void formers, which reduce the amount of in situ concrete that's needed and help increase the span. And I think these were around 12 meters, which is pretty good. And this is what it looked like once those floor units were in position. And it's very high quality finish. They specified a concrete mix with 75% white cement to give a nice light finish. And hopefully you can see on your screen, if you look to the left and to the right on that soffit, you can see that these structural columns are reflected in the soffit, which gives you an idea of the quality. Now, the use of white cement did add costs to the project, but there were savings, of course, from not needing to paint the soffit. The pipework is supplied from a borehole, and water comes up at around 14 degrees. The soffit itself at the surface is about 20 degrees, and they maintain that year-round, and that's enough to ensure that the internal temperature of that space remains between 20 and 26 degrees across the year. And just finally, this is the CAFOD headquarters in London, which also has water-cooled soffits. The difference being here that these are in situ floors, just cast on simple plywood formwork and then painted white. The pipework design is done by Velta, as it was at the business school, which you've just seen, and they are the market leaders in designing this type of system. And the final point really to make is that this building and a lot of others with these techniques, although they've got mechanical systems, some have air conditioning, they try and use the passive approach as much as possible, and they only resort to mechanical ventilation when necessary. This building and the last one use a borehole. That will work all summer, and then it's connected to a heat pump during the heating season, so you can boost the water temperature and also use the soffits for radiant heating, so it's very much a year-round system. So you'll find both these case studies in that publication, and here it is again, and there's the link if you want to download that. And finally, just a quick plug for our concrete and masonry pavilion at EcoBuild, which runs from the 3rd to the 5th of March. We are going to have daily seminars and talks, virtually back-to-back actually. It'll be speakers from the Concrete Centre, and we've got guest speakers as well, covering loads of topics. And you'll find the seminar programme on our website. And also, we've got lots of things to look at, including some games made from concrete. We're going to have checkers, noughts and crosses, and I think there's going to be a concrete jigsaw as well. So if you're up there, do come by and take a look, and hopefully see you there.
Brilliant, wonderful. Thank you very much, James. Very interesting presentation. Right, we've reached the end of the 3 presentations, and we're now in the questions Q&A session, so please carry on continuing to ask questions, send them in, and then we'll present them to the various assembled panelists. While you're all still doing that, I'm going to get in one question of my own. I suppose I'm going to open this out to the group. Obviously, it's slightly unfair, seeing as obviously the subject matter of what we're talking about today is office buildings, but I'm going to ask it anyway. Obviously, as you've all shown, there are clear advantages with this kind of construction for office buildings, the commercial sector. Would you say those principles of low carbon sustainable concrete can be easily applied possibly in other sectors where you don't necessarily have a requirement for or a necessity for chilled beams, exposed ceilings, large cooling loads such as residential, for instance? Or would you say this particular kind of concrete use is optimized for the commercial office sector? If anybody would like to grab that.
I'll take
Okay,
that one
over to you.
Okay. Yes, it is certainly very well developed in the office sector, and in some respects I think the housing sector has got some catching up to do. But given the effects of climate change and the problems we're having recently with overheating, I think it certainly can be used. Thermal mass has a great deal to offer in respect of minimising overheating, but it is of course very important to have good ventilation, and that I think is actually the key challenge. The thermal mass comes as a bonus once you've sorted out the ventilation issue, and by that I mean security, noise, pollution from the street. So I think we need to pay a bit more attention to how we design ventilation systems, particularly in urban residential units.
Okay, all right. Cheers. Thank you, Tom. Yeah, Jay, you got something to say, Jerry? Go ahead.
The question of residential in particular is quite a broad one, because probably we're sat here in central London and we're thinking high density residential. It obviously varies quite a lot, whether it's a detached house in a rural environment as to a city centre environment. We tend to find that concrete is the default material that is used for high-rise, high-density construction because of a number of benefits that you get from it. Fundamentally, the acoustic performance is excellent, and it allows you to complete the build and seal up to the floor soffits more easily. So overall, there's often program benefit which is in amongst there. What we do find though is that thermal mass is less well utilised because the approach in recent times has been to have very, very well sealed environments for the residential, where heat recovery is used to minimise use, but it's still certainly usually the preferred approach to high density.
Okay, all right, great. Okay then. Right, it's enough for me for now. I'm going to start presenting some questions to the panelists. Now we've received a number of questions asking about formwork and how, obviously, with this emphasis on exposed concrete, how that kind of quality is maintained. So I'd like to ask the panel, if James has expressed an interest in maybe speaking about this, how is the issue of formwork and maintaining that exposed aesthetic quality achieved with regards to this use of concrete? James.
Thank you. I mean, it's not an easy thing to achieve, and I think with the 5 Pancras Square example, we went to great efforts to get the finished article. The modular system which we used to create the soffits was called a Topic system, which is a German system which is based on a 1.8 by 1.8 meter grid. Now this is effectively a series of interlinking tabletops which are supported from the floor below and a series of reinforcement bars and concrete are poured on top. Now we weren't too sure about this at first. It was kind of led by the contractor, and we went to a number of buildings where it had been used before to see how it looked, and we also created a mock-up. So it was a process just to see how things looked, and in the end we were quite happy with the result. I think particularly when you're exposing thermal mass and you're kind of suspending fittings and services beneath that, you're not immediately looking up at the soffit directly, so you've got a little bit of distraction there as well. So yeah, I think ultimately we were very pleased with the formwork and the way that looked in the end. I think sometimes architects can be very precious about that, and I think sometimes you have to take a balanced approach about how things look and the benefits that you can derive from the forms of construction.
Okay, great. Yeah. Jerry?
I think actually, again, it's quite a wide question because many people and architects and building users will have a difference in view of what concrete should look like. Yeah. Should it look like concrete as struck and the imperfections, warts and all, be there and be acceptable? Which is, it's very popular for people to take on warehousing building where they openly accept the fact that these blemishes are there, yeah. Or do we put a great deal of effort into making it a real architectural feature of the building, and they are completely at different ends of the spectrum in terms of the process that you would implement. We have a great deal of experience in trying to achieve both. If you are targeting the higher end, the higher quality end of that spectrum, then it is incredibly important that you work with contractors who are experienced in doing these things, because the process has to be perfect every single time you do it. So every pour has to be done again and again and again. The accuracy of the formwork, the joinery, is absolutely of the highest importance, and you can't get good concrete without good formwork, and the testing, the prototyping, and making sure that you can achieve that is exceptionally important.
Great, excellent. Okay, thank you.
Just add that the importance of specifications in all this as well.
Yeah.
You need to make sure you capture the quality and what you envisage in your spec.
In the spec.
Yeah, exactly.
Right, okay.
That's an important consideration.
Wonderful. Right, okay, go ahead.
Yeah, hi. Can I just add that the Concrete Centre is just about to publish a guide on visual concrete, which will give you lots of guidance on how to achieve the kind of finish you want. And it's also just worth mentioning there's precast options as well, which can take a little bit of the risk out of it in terms of the quality of finish.
Okay, thanks, Tom. Actually, while we have Tom's attention here, we have another question from a chap called Daniel Hayward, who has asked, are there comparative user comfort studies undertaken in the building using the active passive cooling using the active passive cooling present in the exposed concrete soffits versus similar buildings utilizing natural and mechanical ventilation or cooling. So, if you wouldn't mind addressing that.
That is the holy grail of questions, because I think the answer is there aren't many studies at all. Like most things, nobody wants to pay for post-occupancy evaluations. So yes, information is a bit thin on the ground. Having said that, if you were to look at the guide I mentioned earlier on passive and active cooling with concrete soffits, in the case studies, some of the clients have done some monitoring to see how their buildings perform. But I don't think anyone's done a comprehensive review comparing one approach with another. Well, not yet, anyway.
Right, okay. All right, okay. Okay, we've had a couple of questions, again maybe slightly unfair, we're in an office in London, but we've had a few questions about how easy it is to apply this kind of concrete, this kind of construction system in a different kind of climate, say a tropical climate. How easy is that? Can this kind of use of concrete be applied in different climates different to our own, easily, or not?
The key answer to that is it depends on the diurnal temperature. If the difference between the average daytime and nighttime temperature isn't very much, then you're not going to get any benefit from heavyweight construction. You really need about 10 degrees or more between the average daytime and nighttime temperature, so that you can drive that heat out of the concrete at night. And if you haven't got that, then the concrete simply gets saturated with heat, and you can't shift it. And you'll find in tropical climates, if you look at the architecture there, it'll suit the climate, and it'll probably be lightweight. So it's all about the climate and the diurnal temperature.
Okay, all right. Okay, excellent. Had a few questions talking about lifespan of these buildings as well. Another one here which is asked, what is the predicted lifespan of the building? Oh, I suppose he's referring to say 240 Blackfriars, for instance. What happens to all the concrete when the building is demolished? Can it be reused or recycled effectively? Are there any characteristics of this use of this kind of concrete which makes that kind of long-term embodied energy argument even more efficient?
Yeah, well, firstly, concrete frame buildings will last for 80 years plus, so they've got a very long lifespan, and increasingly they are being stripped back to the frames these days and fully refurbished. It makes, in most cases, good economic sense, and good sense from a whole life CO2 perspective as well. In terms of when they do reach end of life and are demolished, all concrete in the UK is reused and recycled. I've recently been working with the Association of Demolition Contractors and looking at their waste returns, and there's no evidence of any concrete really going to landfill at all. Most of it is used on site for whatever follows on from the original building, so it'll be used in groundworks. A small amount goes off-site. Very little is used in new concrete at the moment. But I guess the key point is, it's not wasted. And another interesting fact you may not know is that at end of life, when the material is crushed up, it carbonates quite rapidly, because what that means basically is it absorbs CO2 from the atmosphere. And it's able to do that because when you crush it, you massively increase the surface area. So there's actually a take-back of CO2 at end of life.
Okay, all right.
I
Jerry,
think,
go ahead.
It's an interesting question, because concrete structures have been around for centuries, millennia even, to be honest. The only thing that generally causes us issues in terms of their longevity is the steel that we put into it. It's what tends to deteriorate most quickly, and if you have to have concrete in aggressive environments such as in the ground where it's exposed to basically acids taking the alkalinity out of it, then you can eventually end up with concrete corrosion. But I think that there is a swing away from the idea, I think, that we should be taking down buildings and demolishing them, and more people are recognising that the idea of long life loose fit is much more appropriate, and that there should be flexibility designed in trying to take account of what the future needs of the building will be. And actually BREEAM's even guiding us in that direction now,
Yeah.
telling us that we have to think about the impacts of climate change when we design.
Okay. All right. Thank you. Great. We have hopefully maybe a simple question here. It's from Chris Mole, and he simply asks, what are the maintenance challenges with mechanical cooling within the concrete? So are there any particular unique maintenance challenges to do with embedded cooling pipes within concrete? Tom?
Yeah, I'll take that one. No, not really. It's a very, very low maintenance system. The water coming out of the boreholes will typically go through a plate heat exchanger, and that keeps the water circuit in the boreholes separate from the services within the building, so you don't get any contamination there. The polybutylene pipe work will last indefinitely. The only danger is that you might inadvertently damage the pipe when you're installing the slabs. But what they tend to do on site is to issue shanked drill bits to the contractors, which means that when they're drilling into the soffit to mount things, the drill cannot reach the depth of the pipe work. And typically the pipe work, as I said earlier, it's all installed precast factory for the precast option and pressure tested there, and it remains under pressure on site with a pressure gauge, so that you can monitor the integrity of the pipe work and make sure it's not damaged. So I think the short answer is no, it's very low maintenance and extremely low risk.
Okay, all right, great thing. I mean, kind of leading on from that, we have another question here from a James Griffiths. I'm afraid it's asking about comparison studies once again. Have there been any full comparison studies, he asks, for comparing exposed soffits with embedded pipework versus comparable HVAC systems? Sorry, I do seem to be picking on you. A lot of these questions. Go for it.
Not that I'm aware of. There may be, but I haven't come across such a study. To some extent, it's comparing apples with oranges, because buildings with pipes embedded in the soffit are slightly more free running, so you'd expect the internal temperature to be allowed to vary more than you would in an air-conditioned building where you've got tighter control. But in terms of CO2 emissions, I have looked at a whole range of passively cooled buildings with concrete floors and added up the average CO2 emissions, and it comes out at about 40 kilograms per metre squared per year for the kind of buildings I've been talking about, which compares to around 75 to 80 kilograms per metre squared for a good practice air-conditioned office. So it's roughly, this is very roughly because obviously it varies from project to project, but it's roughly about half the CO2 emissions.
Okay, all right, quite wonderful. Okay, I suppose I'll have a wider question to the panel, and this concerns, I suppose, the question of aesthetics. Obviously, in this room, we all love concrete, and we're all fully conversed with the kind of benefits and advantages it gives. But there is maybe still a perception among some in the public. Obviously, the term like concrete jungle is used as a term of derision, and some people wrongly now still associate concrete with maybe the negative aspects of development. What do you think, if at all, low carbon sustainable concrete can do in terms of kind of improving and revitalizing and kind of enhancing the image of concrete from a kind of visual point of view amongst those members of the general public who haven't yet been as converted as we are? James.
Yeah, I think it's all about how you use it. I think the term concrete jungle was quite often a case where there's just so much concrete used in one space or in one building all at the same time, and it just could be a little bit too monotonous. And I think you have to use it selectively. And I think with Pancras Square we were keen to try and use it effectively, i.e. kind of exploit the structure or make the structure very, very clear through the use of concrete. So, it's I think you have to be clear about how you use it, not overusing it. Car parks use it very well, but we don't want every building to look like a car park.
Right.
Exactly. Yeah. So I think.
Okay. All right. Thank you. Great. A few more technical questions before we close. We've seen one here from Adrian Moore. With a chilled slab, is there any way to control, raise or lower temperature to individual zones and rooms?
Yeah, absolutely. You can zone it any way you like, really. And the beauty of it is that if you vary the temperature of the water in your pipe work. You'll get a change in soffit temperature within about, I think it's about 20 minutes to half an hour. So compared to just having a system with natural ventilation or mixed flow ventilation, you've got much more rapid control. So yeah, the answer is you can do it.
Okay, all right. We've got another technical question here from Sangmok Kim. Cooled surface sealing, it may seem quite simplistic. Doesn't it get condensation when internal air gets into contact with it?
No, you design it so that can't happen. The lowest temperature you can supply water at to prevent condensation forming is about 14 degrees. If you went any lower than that, then yes, you do run the risk of condensation forming under certain conditions. So that is the limit, and no one really goes below that level. But the good thing is, water coming out of the ground from your borehole it's about 12 degrees, and once it's gone through that heat exchanger I mentioned earlier, it's about 14 degrees, so it's the optimum temperature. But you certainly, you don't want to go any lower, and condensation is a concern. So that has been thought of, and you just limit the flow temperature.
Okay, all right, thank you. We have another kind of, I suppose, technical question, which applies to 240 and 5 Pancras Square. What finished floor-to-ceiling height was achieved in the office areas, and how much lower would it have been with the same floor-to-floor ceiling height using the more common suspended ceiling solution? So what advantage did it offer in terms of floor-to-ceiling height?
I'm quite happy to take this one first. I think from memory we had just over 3 metres floor to exposed concrete slab in the offices at 5 Pancras Square, and which was a generous kind of amount of space. And I think if we'd struck a line from the underside of the suspended services, we would have ended up with about 2.6 metres internal height. So
right.
It does have a significant impact on the internal environment if you do add a ceiling into those spaces. So, obviously there was an element of seeing kind of a few pipes and wires behind secondary rafts and within the lighting rafts. But to be honest, your attention isn't really drawn to that when you're in the space. It's more a case of the overall impression you get from the office environment which you take in. So quite a significant kind of height difference there, actually.
Yeah. Okay,
and
all right.
240 Blackfriars actually does have a suspended ceiling in it. It's 2.7 floor to ceiling. The building, the approach is quite different because in many ways 240 is a speculative office building which has to respond to the potential needs or requirements or desires of many separate tenants, whereas 5 Pancras Square already had a client lined up who we could have discussions with about these things.
Right, okay, all right. I suppose in a way, leading on from that, we've had a couple of questions here from Manhal Saeed. It says here, many architects use suspended ceilings, not through choice, but how does this affect the performance of thermal active concrete slabs? And I suppose that can be applied to 240 Blackfriars as well.
Well, we don't have thermally activated concrete slabs in 240 Blackfriars. There are ways of using the thermal mass within the slabs. It tends to be when it's coupled with a displacement vent system, and you can use the top surface rather than the soffit of the slab to take the heat out.
Okay, all right. Okay then. Yes, go. Sorry, Tom. I just missed it.
Yeah, no, suspended ceilings. There is an option of using open ceilings or perforated ceilings as well. So you've got some exposure of the concrete whilst perhaps not being able to physically see the soffit. So that's a sort of a compromise solution. It's good, but it will impact on the thermal mass performance to some extent.
Okay, all right then. All right, final question. Maybe hopefully another simple technical one to answer. Are there any acoustic, or were there any particular or specific acoustic issues to do with the use of this concrete that arose in either buildings, 5 Pancras Square or 240 Blackfriars?
Well, with 5 Pancras Square, I think, yes, you always run the risk that having a lot of concrete on display means that there's going to be a lot of sound bouncing around the place. But we used acoustic matting on top of the secondary raft, which housed the lighting, carpeting throughout, and a lot of the freestanding furniture within the space was heavily fabricked, so it had an impact on kind of taking some of that sound out. And I think often the introduction of people helps spaces work quite well. there's a bit of background noise generated by the occupation, which tends to work quite well. So, yeah, we were aware of it, but we wanted to downplay that as much as possible.
Great, thank you. Thank you very much, Dave. I'd like to thank all our panellists for their expert opinion and input on this morning's webinar. Hopefully it's been of use and interest to all of you listening. Thank you very much. This webinar will be available on the website. It will be available on demand for the next 12 months, to be able to go back there and revisit it. So I'd like to thank our panellists. I'd like to thank our sponsors as well, our partner, at the Concrete Centre. I'd like to thank you all very much for listening. Thank you and have a good day.